Welcome to the video of part 4 in the subject Computer Vision, Unit 3 Future-Based Alignment and Motion Estimation. I am Dr. K. Padmapriya, Assistant Professor, Department of ECE, Government College of Engineering, Tirunelveli. In the previous video, we saw about two-frame structure from motion, and in this part we can see about the techniques which we follow for the multi-frame structure from motion. And in that, the main technique, first technique we are going to discuss about is factorization. And in the earlier video, we saw about the two-frame structure from motion. So in structure from motion, we are given a set of feature tracks and we estimate the 3D structure and 3D camera motion. And the assumption what we make is orthographic projection, and the tracks UFP and VFP, where F denotes the frame and P denotes the point, that is the position of it. So subtracting out the mean 2D position, you get the relation for U and V, that is for the particular frame and for the particular position. The U comma V will be UFP VFP, which is equal to IF transpose into SP, that is the position. So P is the point and the S is the position for that point. So IF gives the rotation. So this denotes the rotation and the position. So U comma V will give you the tracks for the camera position, U comma V camera parameters. The measurement equations are UFP, IF transpose SP and JF transpose SP. So rotation and IF and SP are the rotation and position respectively. Stacking all the different positions of U comma V, we are stacking them up and we get the representation as W equals R into S, where R are the sets of rotations for the different frames of I and J, and S is the set of all the positions S1 to SP. So this is how you do the factorization using single vector decomposition. So W will be U cap V, and this must be your ranking, always it must be 3. So this should be always orthogonal, your R and S. So your orthogonality is satisfied when you satisfy this condition. And by shaping the factorization, this is the final equation of the projection of n features in one image. U1 up to Un, which is equal to pi of product of your x1 up to xn. So this is a 2 cross n matrix and this is a 2 cross 3, which here this is a 3 cross n matrix. So projection of n features in f images. This is for a one image, that means one row like thing. So here you will be having for f number of images. So all these will be twice f into n, twice f into 3, and this is 3 cross n, the same S matrix. So your W is your final measurement, M denotes your motion, and S denotes the shape. So generally it is mentioned in this notation. And the key observation is your rank of W, it should be always less than or equal to 3. So this is the general notation for the previous matrix. So W, M and S are used to mention it. So how you find the shape? By the factorization method. So this is known and you have to solve for this right hand part. So factorization technique, your W is at most rank 3. So if you have no noise, then it can be assumed to be 3, and we can use SVD method for factoring the F, that is singular value decomposition. So W will be, this is the equation M dash S dash. So it is the expected values of it. So SVD decomposes any M cross N matrix capital A as A M cross N, which is equal to U M cross M summation M cross N V transpose. And the property summation is the diagonal matrix containing the eigenvalues of A transpose into A, which are known as the singular values of A. Diagonal entries are sorted from the largest to smallest. So columns of U are eigenvectors of A into A transpose, and columns of V are eigenvectors of A transpose A. And if A is singular, so these are the conditions. So your 3 singular values will be non-zero and throw away all but the first 3 columns of U and V, and you have to choose m dash which is equal to u dash, s dash is equal to summation dash v dash transpose a mn, which will be equal to u dash summation dash and v dash transpose. So this is how we factorize it and finalize that with your W. So this is your final equation for. So you have to solve for A by enforcing the metric constraints on B. And the metric constraints for an orthographic camera, this is your rows are orthogonal. So pi into pi transpose will be this value where your diagonal alone unit matrix, your diagonal alones are unitary matrix. And weak perspective camera means this is your orthogonality condition. You will have conjugates here and enforcing metric constant. So you have to compose the A such that the rows of M have these properties. So constraints are linear in A into A transpose. So this is the condition, and finally you can have the condition that is G equals A into A transpose by singular value decomposition since U and V are equal. So factorization with noisy data means you add up this error factor to the actual equation, and your error factor is 2f cross n. So once again you use this SVD of W. So all the first three singular values to be 0, which will lead a new matrix W dash, and that will be having a rank 3 approximation of W. So the final value of W will be, you will be including the error factor also. So you estimate the W dash, then use noise-free factorization of WS as in the previous technique without noise how you did. So result minimizes the SSD between positions of image features and projection of the reconstruction. So the extension of them are independently moving objects, perspective projection, outlier rejection, subspace constraints, SFM without correspondence. How you extend this factorization to this perspective projection. So for that, ortho weak perspective model have to be used, and then it has to be iterated. And in the next method from Christie and Horrod, they derived the expression for weak perspective as a perspective projection. So this is the equation for it. The basic projection procedure is you have to run TK model with weak perspective, then solve for the sigma I and for different each row of M, and add correlation term to W, solve again till it get converged. So perspective and projective factorization. So disadvantage of your regular factorization is that it cannot deal with the perspective cameras. So one way to get around this problem is to perform an initial affine reconstruction. Of course it should be orthographic, and to then correct for the perspective effects in an iterative manner. So this algorithm usually converges in 3 to 5 iterations itself. So with the majority of the time spent in SVD computation only. An alternative approach which does not assume partially calibrated cameras, known as image center, square pixels and zero Q, is to perform a fully projective factorization. In this case, the inclusion of the third row of the camera matrix in the measurement matrix is equivalent to multiply each reconstructed measurement. And in any case, it is unclear when a fully projective reconstruction would be preferable to be a partially calibrated one, especially if they are being used to initialize a full bundle adjustment of all the parameters. One of the attractions of factorization methods is that they provide a closed form, and sometimes it will be linear method also, to initialize iterative techniques, and this is called as bundle adjustment. So an alternative initialization technique is to estimate the homographies corresponding to the common plane seen by all the cameras. In a calibrated camera setting, this can correspond to estimate the consistent rotations for all of the cameras, for example using matched vanishing points. Once these have been recovered, the camera positions can then be obtained by solving a linear system. And it can be recovered with the camera positions, and that can be solved by the linear system. Bundle adjustment. So bundle adjustment, it's a technique for simultaneously refining the 3D structure and camera parameters. So it's capable of obtaining an optimal reconstruction under certain assumptions on image error models. So for zero mean Gaussian image errors, the bundle adjustment is the maximum likelihood estimated. So this diagram, it shows the incremental structure from motion. So it's a technique which is used in the bundle adjustment. So here we start with initially 2-frame reconstruction, then batches of images will be added using post estimation and their positions will be refined using the bundle adjustment. So at the final, so initially you can see you have less clarity with the picture. When bundle adjustment has been made and you are finding exact reconstruction of it, so now you have reconstructed a better picture than the initial one. And in bundle adjustment, n 3D points are seen in m views. So m cross n you will be getting. So your n number of m views. So xij is the projection of ith point on the image j. And aj is the parameter for the jth camera and bi is the parameter for the ith point. So bundle adjustment attempts to minimize the projection error. So this is the equation minimizing with respect to ai and aj, bi, summation of I equals 1 to n and summation j equals 1 to m, d of q aij, comma bi, comma xij, all the whole square. So this denotes the Euclidean distance and q represents the predicted projection. So in bundle adjustment, we construct the 3D to 2D mapping with the function of intrinsic k and extrinsic camera parameters r and t. And measurement will be affected by noise. So ui and vi, it will be a function. So normally we will be giving as a function of kr txi. And here since we have u and f, so you use f and j. Both are functions. Plus the noise. This is the noise for u and this is noise for v. So ui cap plus ni, vi cap plus mi. So the noise which you assume is having that is n of 0 comma sigma. So log likelihood of krt. So given for the sets of list any number of u comma v pass. So C will be equal to minus log L and this is the equation for it. So the difference between the actual value and the estimated value, the whole square divided by the variance square. So minimized via non-linear least squares regression, which you call the bundle adjustment. So an example of it is Levenberg-Marquardt. And this is what the U cap and V cap equations for IJ, and this makes non-linear minimization very hard. So many more parameters will be included, which makes it potentially slow. So poorer conditions since we have high correlation among them, and potentially it have lots of outliers, and gauge freedom, coordinates freedom will not be there. So all these are the drawbacks of the bundle adjustment. And when you have a number of parameters, so what we have to go for? So sparsity will be increasing. So this is the case. Your list of your uij cap and vij cap. And here are the Jacobian which are non-zero. Take it, and this is your Jacobian matrix representation. This is Hessian. So this give the pictorial representations of the Jacobian and Hessian. And here it gives the bipartite graph for a toy structure from motion problem. And this is the Jacobian J and the Hessian, that is which has been mentioned here. This, with here it has been mentioned with the corresponding values, and the same picture when you compare for this toy structure. So the numbers indicate the 3D points where you have, that is 1, 2, 3, 4, etc. And the letters indicates the camera positions. So A, B, C, D are camera. So 4 different cameras at 9 different positions. So the dashed arcs and light blue squares which will indicate the fill-in that occurs when the structure variables are eliminated. So when you eliminate, these are the blue, it is denoted by the camera. So from camera A for the position 1, from camera A for position 2. Similarly with camera B, C, D, etc. with all the positions. So here this is the way how your Jacobian matrix is constructed with for the same structure, and this is an example for Hessian. So Hessian you are having the fill-in and overlapped areas much more. Spatz-Cholesky, that is Kylan, it was used in finite element analysis applied to SFM. So this is how your Hessian matrix is shown, and this is how your natural Cholesky graph is seen. And here if you have poor condition, you have to use the second order method and Cholesky decomposition. So this is how the pictorial differences shows. And gauge freedom, we fix certain parameters with respect to the orientation or zero out all the last few rows in the Cholesky decomposition. So these are the two assumptions which is made to achieve the gauge freedom. And the next technique is robust error models. So outlier rejection, so use robust penalty applied to each set of joint measurements. And this is the equation for it. So for bad data you have to use for ransack. So ransack, it is related to least median squares. So repeatedly select a small subset of correspondences and estimate a solution. Then count the number of inliers, which is modulus E less than capital theta. So for LMS you have to calculate the median. So pick the best subset of the inliers, find a complete least squares solution. And it can refine correspondences, it can refine the feature matching after a structure and motion estimate has been produced, and decide which ones obey the epipolar geometry, decide which ones are geometrically consistent, and iterate between the correspondences and SFM estimates using MCMC. So the limitations are for the structure from motion, it's very difficult to reliably estimate the metric structure and motion unless your X and Y rotation is large and the large field of view and depth variation is present. So camera calibration is important for Euclidean reconstructions, and it need good feature tracker. Global structure from motion. While incremental bundle adjustment algorithms are mostly used for large scale reconstruction, they can be quite slow because of the need to successively solve increasing larger optimization problems. So an alternative to iteratively growing the solution is to solve for all of the structure and motion unknowns in a single global step once the future correspondences have been established. The pipeline implementing rotation averaging and post-graph optimization concept, which includes the initial future point extraction, matching and two-view reconstruction followed by global rotation estimation, and then a final solve for the camera centers. The pipeline also matches vanishing points when these can be found in order to eliminate the rotational drift in the global orientation estimates. So this gives a block diagram for global structure from motion. So first we have the feature extraction, then you feed up all the images. From the images, take the interested points and line segments. Use the two-view matching and vanishing point detection. So to do all these processes, then line and virtual vanishing point matching, and then point tracks and vanishing point tracks are given to the global rotation estimation, then linearly constructed. So vanishing point and feature based pairwise rotation estimates are used to first estimate a global estimation, and global consistent set of orientations will be created, and then the scales of all the pairwise reconstruction along with the camera center positions are then estimated in a single linear least square minimization. So two-view reconstruction, robust alignment, and then global scale plus translation estimation. So constraint structure and motion. Here instead of exploiting the regularity in the scene structure, it is possible to take advantage of a constrained motion model. And for example, if the object of interest is rotating on a turnable that is around a fixed but unknown axis, specialized techniques can be used to recover this motion. In other situations, the camera itself may be moving in a fixed arc around some center of rotation. Specialized capture setups such as mobile stereo camera rigs or moving vehicles equipped with multiple fixed cameras can also take advantage of knowledge that individual cameras are fixed with respect to the capture rig. So in this constraint structure and motion, we have two techniques. One is line-based techniques and the other is the plane-based techniques. And in line-based techniques, the pairwise epipolar geometry cannot be recovered from line matches alone, even if the cameras are calibrated. To see this, think of projecting the set of lines in each image into a set of 3D planes in space. So you can move the two cameras into any configuration you like and still obtain a valid construction for 3D lines. When lines are visible in three or more views, the trifocal tensor can be used to transfer lines from one pair of images to another. The trifocal tensor can also be computed on the basis of line matches alone. For triple of images, the trifocal tensor is used to verify that the lines are in geometric correspondence before evaluating the correlations between the line segments. Extend the three-view relation, that is the trifocal tensors computed from manual line correspondences to a full bundle adjustment of all the line and camera parameters. Use the Plucker coordinators to parameterize the lines and to directly minimize the reprojection errors. It's also possible to represent the 3D line segments by their endpoints and to measure either the reprojection error perpendicular to the detected 2D line segments in each image or the 2D errors using an elongated uncertainty ellipse aligned with the line segment direction. The figure shows the two images of a toy house along with their matched 3D line segments. So instead of reconstructing all the 3D lines, use Transact to group lines into likely coplanar subsets. 4 lines are chosen at random to compute a homography, which is then verified for these and other plausible line segment matches by evaluating color histogram based correlation scores. The 2D intersection points of lines belonging to the same plane are then used as virtual measurements to estimate the epipolar geometry, which is more accurate than using the homographies directly. An alternative to grouping lines into coplanar subsets is to group lines by parallelism. Whenever 3 or more 2D lines share common vanishing points, there is a good likelihood that they are parallel in 3D. By finding multiple vanishing points in an image and establishing correspondences between such vanishing points in different images, the relative rotations between various images can be directly estimated. So finding an orthogonal set of vanishing points and using them to establish a global orientation is often called invoking the Manhattan world assumption. So a generalized version where streets can meet at non-orthogonal angles was called the Atlanta world. So describing a 3D modeling system that constructs calibrated panoramas from multiple images and then has the user draw vertical and horizontal lines in the image to demarcate the boundaries of planar regions. The lines are used to establish an absolute rotation for each panorama and are then used to build a 3D structure, which can be recovered up to a scale from one or more images. A fully automated approach to line-based structure from motion is to find the lines and group them by common vanishing points in each image. The vanishing points are then used to calibrate the camera, that is to perform a metric upgrade. Lines corresponding to common vanishing points are then matched using both appearance and trifocal tensors. These lines are then used to infer planes and a block structured model for the scene. Deep neural networks can also be used to construct 3D wireframe models from one or more images. Constraint structure and motion. So the next we have are the plane-based techniques. So in scenes that are rich in planar structures, example in architecture, it is possible to directly estimate the homographies between different planes. In line-based techniques, we discussed about lines, and here we use the planes to reconstruct it. And either use feature-based or intensity-based methods. So in this principle, information can be used to simultaneously infer the camera poses and plane equation. So to compute the plane-based structure from motion. So a fundamental matrix can be directly computed from two or more homographics using algebraic manipulations and least squares. Unfortunately, this approach often performs poorly because the algebraic errors do not correspond to meaningful reprojection errors. So to hallucinate the virtual point correspondences within the areas from which each homography was computed and to feed them to a standard structure from motion algorithm. So full bundle adjustment is used with explicit plane equations as well as additional constraints to force the reconstruction of coplanar features to lie exactly on the corresponding planes. The direction of lines and normals for the planes in the scene are pre-specified by the user. So planes are used as additional constraints inside the bundle adjustment formulation. Combinations of lines and planes are used to reduce the drift in 3D reconstruction. So in motion estimation, we have translational alignment, parametric motion, spline-based motion, optical flow, and layered motion. And we can discuss about only translation alignment in this video, and the other parametric motion and the remaining part we can discuss with the rest part of the video.